Hello and welcome back to Calculus 3. So section 11.5, lines and curves in space. Now we are going to define a line in tridimensional space and take a look at the way it works. First, we have to define something that is called a vector valued function, and then we are going to use that to figure out the equation of the line in 3D. You are used to seeing the 2D line as y equal mx plus b. This will have a very similar form, except obviously for 3D. So we start with the definition of a vector valued function. So vector valued function is going to be a collection, it's going to be a vector, which is a collection of functions for each of the dimensions. So vector valued function R would be defined as a vector of f of t, g of t, and h of t, say for three-dimensional vector valued function. And you already seen this in the shape of parametric equations. So I'm just going to leave this at that. It's simply a collection of functions, one for x direction, one for y, and one for z. Now they're all in terms of parameter t, and you can think of this t as evolution in time. So now that I have this, I'm going to do this, and I say parametric equations. And I'm already connecting this to your chapter 10, right? Calc 2, you already learned what the parametric equations are. So we already know what this is. We are just putting a different name to it, right? Rebranding it technically. And we are going to now just quickly look at this and understand it the best we can. So for the 2D case, right, if we go back to 2D, when I say y is equal to, let's say, x squared minus 2, you remember that there is associated graph, right, in this case going to negative 2, and you are able to find points on this curve which are locations where you could potentially be. Please remember that I asked you in this class to look at the floor and realize that is your good old XY plane on which you can walk upright. So I can draw on the floor this curve and I can walk along it. Now, generally we say, well, just let the ant walk along this path, which is on the floor. So the 2D case is the subset of the 3D, right? And we are just looking now at the 2D case. So if I want to find the location, let's say at x equals to 3, the location is going to be 3, 7. Because 3 squared is 9, minus 2 is 7, so x coordinate is 3 and y coordinate is 7. But we also talked about parametric equations, and we said that for this particular case where you actually already have a function, it's not necessary to at all do the parametric equations, but you can, right? So we said we can just quickly get the parametric set by writing y equals t and then y equals t squared minus 2. And you can clearly see that if you plug in the t equals x, right, in the second equation, you're getting x squared minus 2. So now if you have this situation or the parametric equations, now I would like to think about this set as the set is dependent in time, right? And it makes so much sense to think about, okay, at time t equals 0, where am I, right? At time t equals 0, I am going to be at x equals 0 and t equals -2. And that is location in space, right? It's a location on the floor at which I am standing. In this case, it would be the vertex of the parabola which I drew on the floor. And then you can ask yourself at time, let's say t equals to 5 seconds, where am I? I am at 5 and then 23, right? Again, it's another location in space. So if I call the location here, right? If I call the location right where the projector is -2, 0, which would be the vertex, and you have the parabola going that way, I would have to go 5 feet this way and then 23 feet that way to get to location 523, and I will achieve that in 5 seconds, right? So you can see the dependence over here on the parameter. You change the parameter, which you can understand it as time, and you will be at different locations. So now, having this parametric set, the new vector valued function, which I defined up there as a set of the parametric equations, which is a set of functions, the third representation now of this 2D y equal x squared minus 2 would be to write r, which is the vector valued function, would be t comma t squared minus 2. So now you have all three representations for the same line. All three of these representations are the same, except you can see the blue and the red over here are actually the same, it's just a different notation, and we put a different name. Parametric equations, and over here we call it the vector valued function, which is a set of parametric equations placed in a vector. Now, it has the same properties, it does all of that the same, except it gives us also another perspective, and that is that there is this vector r which stretches from the origin to the point that you are tracing. So it's a single vector that is tracing your motion through the space. So what would that look like? So if I am to graph this and then try to see what this vector actually does, let's first draw the parabola. And we have our origin 0, 0. And I'm just going to place few of these points along the line. Now this obviously goes forever. And now I am going to draw vector r. So as you can see, so all of these are obviously vector r, because vector r is now a function. See? Vector is no longer 3, 7. Because vector 3, 7 just points to, from origin, points to point 3, 7, and that's it. This vector is changing all the time, right? The magnitude of the vector and the direction of the vector change as the parameter t changes. So vector valued function is going to give you a vector as a result, right? A vector as a result when you plug in your t and your in these components. So now, if I am to compute, what's happening at the time t equals 0, the output is 0, -2, which is a vector. At time t equals to 5, I am getting 523 as a vector again. So it's not just the location in space as 523 as a point, as you have up there with the parametric equations. Now it's also a vector that points from the origin, and you can calculate the displacement from the origin, the distance from the origin, and all of these things. All this and displacement in this case are the same. So it's a more powerful concept than just a point. right? It's a more powerful concept than a point. So I hope you understood the upgrades that we did progressing in 2D with a familiar function. We start with a basic parabola, y equals x squared minus 2. We understand that. We know that, you can x equals 0, x equals 5, whatever, x equals 3 in my case. And you know there's just a point at that one location, and technically that's it. Then we do a little bit of upgrade, which is the parametric equations. We write the set where each dimension is represented in terms of a parameter t. You can understand t as time. As you let the time flow, right, you can get the same graph back. Now you are gaining one more degree of freedom here, because as your time flows from negative numbers to positive numbers, or as time progresses forward, you actually have the orientation in which the line is drawn. So clearly over here there is no orientation of any kind, because you don't have a degree of freedom for that. In the case of the y equals x squared minus 2, you have 2 degrees of freedom, 2 dimensions, x and y, and both of those are taken to actually figure out the location, right? But when you move to parametric set, you have still x and y dimension, and you are introducing the third, it's not a variable, it's a parameter, and that third thing, parameter in this case, is going to be another degree of freedom which can give us something. And it actually gives us the orientation, which tells us that this parabola flows from left to right as t increases from negative numbers to positive numbers. So that's the upgrade, because you are still obtaining all of the points that you want. As you can see, you are still obtaining the points, but you are getting an extra piece of information, which is orientation. And then with the vector valued function, we upgraded again. So now you still have your parametric equations, right, which are the same. They are now in a vector. So now you're not just getting the points and locations, which you definitely do. You are, and not just orientation, in which way the vector will swipe to trace the curve. You're also getting vectors in addition to that, right? So now the distance to the origin and so on. So it's like a third upgrade, or a second upgrade to the basic case you learned in PreCalc 1. So now that we hopefully understand a little bit better the way these guys work, we can go and build the equation for the line in a straight line in 3D space. So straight line. Well, it's just a line, because the other lines that are not straight are called curves. So I'll put the straight line in space, meaning we are focusing on 3L over here. There are 2 points. We are going to call these P0 and P. P is going to have X, Y, and Z. And this is going to be X0, Y0, Z0. And we are going to have vectors.
What's the other point? P1?
P0, P0. And we have our origin over here.
Is that going to count like as the initial?
Hmm?
That's not like initial line.
Yeah, it's just one. Yeah, one of them. Okay. So when you are looking at this diagram, right, if you try to ignore the red and the blue and just concentrate on everything that is in black, you clearly see the 3 axes there, and you see the line L, which you are trying to figure out the formula for, and you see the 2 points. Now, you should know from your everyday life / common sense that all you need is 2 points to describe a line. And it shouldn't take too much brain power to figure out that that's good for any dimension, because line is completely described by pinning 2 points. You can stretch a piece of rope in 3D space, right? Between 2 points. You can draw the same thing on a paper. If you have 2 points and a straight edge, you can stretch the line between those 2 points, and the line is 100% contained, right? So straight lines in whatever dimension, including the dimension 27 and whatever else, you have 2 points. You have to have 2 points that are fixed in space, and as soon as you fix 2 points in space, you can draw the straight line, and only one way draw the straight line through those points. So now if you are observing this case here, I hope that you see that the slope of the line, the steepness, the orientation of the line in space is completely determined by the vector which stretches from points between points P0 and P. Do we all see that? I did not draw that vector yet, but there is a vector which stretches from P0 to P. And that vector has the direction, right? Not the magnitude. Remember, magnitude, the length of the line is infinite. The line goes forever in all directions. The vectors have finite length. They have the magnitude, right? So we don't care about the magnitude of this vector. We care about its direction, right? So with this green arrow, I am going to indicate over here vector, which the book calls vector v, right? And that vector v is going to be the one that carries the slope, right? And now, here's why you paid money for this course. Ready? Y equal mx plus b. Do we all know this equation? Better. Otherwise, quit today, right? Now look at this. R equals V t plus R 0. Try to stare at this and see if it makes sense. First of all, I want you to see one-to-one correspondence between the symbols we have. 4 symbols in your Algebra 1 equation and 4 symbols in Calculus 3 equation. It cannot be any other way, except the one that you have over here can be any dimension you want. Clearly, we're going to use it for 3D, for our Calc 3 class. But you can have this. This is also an equation that works in 7-dimensional space. Because this equation over here has vectors, and vectors can have any dimensions. You give me a 2D, this equation collapses to the equation over here. We are going to use it as a 3D equation. So now as you're looking at this, right, you say, all right, so I'm looking for the point which has x, y, and z, but because ultimately you want to have x, y, and z in your equation for the line, right? So that, to me, seems like I'm trying to get to that point, which is this, which is that. Now, I need to have a slope, and since the line is what I'm looking for, that slope, the 3D slope with my air quotation marks, is clearly the green vector v. Everything is happening in time. That's the main variable, right? Because we already seen how the time, which is the parameter t. You don't have to have, doesn't have to be time. It could be anything, right? This can evolve with the number of rabbits in a habitat. It's fine. You can have anything as a parameter, anything that can count, right? I don't want to say count in time. Count. And then we have the initial place where everything starts, which would be that. So you can think of that it starts here, it ends there, right, for the vector v. And then, so I hope you can see this one-to-one correspondence. So now, what is vector r? Well, vector r is the point which has coordinates x, y, z, minus the origin, which has coordinates 0, 0, 0. So vector r is clearly the vector that has x, y, and z in it. And vector r0, the red one, is clearly the vector x0, y0, and z0. Do we all see that? Good. Now we are going to define the vector v to have the coordinates a, b, and c, which is going to be the orientation. We'll see the way we get all of these. And now, as you put these guys together, what do you have? I am going to write these vectors now as column vectors. So I have x, y, and z column vector, which is my r, is equal to vector v, which is a, b, c, times the parameter t, now this is my vector v, plus the initial vector of x0, y0. So this is the entire equation written out as the column vectors. Well, instead of writing them horizontally, you write them vertically, and you call it a column vector. That's what it is. And now I just want you to read the first line, and you read the second line, and you read the third line. You see what you get? So the first line is going to give you x equals at plus x0. Second line is y equals bt plus y0. And the third line is z equals ct plus z0. Hello, parametric set of three equations. Right? And now, since we already defined our parametric sets that can be arranged in a vector to give us what we call a vector valued function, the equation of the straight line in 3D in all of its glory is going to be r equals at plus x0, comma, bt plus y0, comma, ct plus z0. This is the one that we are going to use most of the time, but then you can get the other ones as well. Do you get a single equation that you get to write? Yeah, but only as a vector equation. You can't do calculations with it. So this is going to be a level of difficulty that Calculus 3 is going to introduce, and we are going to see this as the course progresses. You are going to use one type of notation and to understand and build concepts, but you are going to use a different form to do calculations. If I wrote this down and told you this is the line in 3D, well, what would you be doing? You would be memorizing this and just using it for problems. Now the same equation is here. Now, does this make sense conceptually? You better say hell yes, because it's one-to-one correspondence to what you know from 2D, right? So you better say hell yes that it makes sense conceptually when you see this equation here. Because you still have your y equals mx plus b, and that's the linear line. But then, all you need to do is to say what dimension I'm in. I'm in dimension 5. That's okay. I have x, y, z, w, and whatever. P. I don't know. You have 5 dimensions, right? And then A, B, C, D, E for this one, right? So you can transfer this and you can extend this to any dimension you want. And I showed you the way you do it. This one is defined in a 3D space or a 5D space. This one and this one. Looking at the points there. And then you write the column vectors, and each line is its own parametric equation, which gives you the equation of the line. So equation of the line in 3D space is going to be the collection of 3 equations. For 2D, you have one equation, y equals mx plus b. For 3D line, you have collection of 3. Unless you want to write it in a vector notation. Now, we are going to use vector notation to develop further concepts. But we are not going to use vector equation to compute anything. Because you can't, right? You have a vector with 3 coordinates and it's just called r. Right? What are you going to do with it? So now, once we have the equation of the line in 3D, we can start having some fun. Meaning problems, right? I go all the way back to our basic algebra 1, right? Elementary algebra. When I say write the equation of the line of Theotel, right? Right? Of Theotel. We all know of Theotel? Well, now you do. So write the equation of the line given m equals 3 and 0.6 and negative 1, right? So now you are in algebra 1, right? You're going back. So you are becoming actually, you're demoted from your 0.5% to 100%. Because 100% of students have to take algebra 1. That is, sadly enough, the New Jersey standard for, right? So everyone has it. But that's as high as it goes. So we have this. Now, what is the way you solve this? Well, you go and you say y equal mx plus b. Y is negative 1. M is 3. X is 6 plus b. From where b is clearly negative 19. And you write your y equals 3x minus 19, and you are done. So you should be able to do this in about 17 seconds, right? Is it going to be different in Calc 3? Well, no, it's not going to be any different. Because, of Theotel again, write the equation of the line. Given that the vector v is, I don't know, 3, negative 1, and 8, right? And given point 1, 1, and 7, whatever. That's not a vector, it's a point. Now, what do we do? Well, you have the point, right? And all you're going to do is you're going to say, fine, I'm going to place my x, y, z parametric equations are going to be vector v times t, right? You have mx, right, which now vt. So we have 3t, negative 1t, and 8t, plus 1, plus 1, plus 7. Hello, column vectors, right? Do we all see that? So hopefully you all see vector v. And then a 0.117.
And then the next one, what was that? Where do you get the +1, +11?
Point through which needs to go.
Oh crap! Yeah.
Good. Now that you are all caught up to that, and I don't have my stick from the other classroom. Can you break one off here now? Vectors are free to move in space. So the vector that you have over there, 3, -1,8, is fixed with its magnitude and its direction, but it's not fixed with the location in space. Now that particular vector carries the direction in which line is going to go. So now you're thinking about the airplane that has its own vector that it's following, right? But that vector could be here, could be here, could be here, right? And that's all free to move in space until a point shows up in space. And then that vector will go through that point. So now, what do you have? You have the direction in which the line has to go, which is given by the slope vector v, and you also have the location in space that bounds this free vector to sit at that point, through that point, right? And now you can just draw an infinite line through that vector. And the line will go through the point. So when I say, find the line going through, and I give you the point, that's the point that fixes this vector. All the vectors are free in space to move wherever you want. Remember this vector, 6, 1? Wasn't that vector earlier right there? And now I'm here, right? So I pick the location where this vector is going to go because the vector is free to move in space. So now you need these two things, slope and a point, and then you're going to have the unique location in space where that vector is going to be, which actually gives us the line. So now, as you can see, I use my slope times the parameter t times time, because it will evolve in time, and then I use the point to pin all of that in space, and I have the parametric equations from where I get my vector valued function. Guys, linear lines are functions. So, vector valued function 3t plus 1, comma, negative t plus 1, comma, 8t plus 7, and then close the vector notation. So this is the answer. That's the answer. So what is the equation of the line? Well, it's all of that in red. Because in 3D, the line has 3 equations. Now, I could, if this was linear algebra class, I could ask you immediately, let's do the 8-dimensional case. And it will be no different. The linear line in 8-dimensional case is going to have 8 of these, x, y, z, and so on, right? So I'm just going to box this, and I'm going to type right here, answer. All right, so this is your equation of the line. Now, it is important also to note that this t is between negative infinity and positive infinity. Because the line is infinite. The line is infinite, it extends to infinity in both directions, right? Because line has 2 ends. And we have to do that with this. Now, we are going to play later on, chapter 14, for instance, with line segments. And the line segment will stretch, let's say, from, I don't know, 1, 1, 1 to 1, 1, 2. And you are just going to have a length of 1 unit, right? in a particular direction. So we are going to eventually mess with this t in a way that is going to limit the line, because we will need line segments. Right now we are working with the infinite line, therefore t is supposed to be from negative infinity to positive infinity. All right, so how do we make things spicier in Algebra 1? Well, if you want someone's head to explode, you ask them to give you equation of the line, but you don't give them slope. You give them 2 points, right? You know. So of Teotel again?
How do you say that?
Of Teotel. Just read it.
Say it 10 times fast.
Yeah, Teotel. So write the equation of the line given, and you have, let's say, 3 and negative 8 and 4 and 6, whatever. It doesn't matter, right? So what do you do in Algebra 1? You say, well, slope is equal to y2 minus y1, right? So you have 6 minus negative 8 divided by 4 minus 3, and your slope is 14. And as soon as you're there, you're happy, because now you have a slope and you have a point, and you can immediately go to y equal mx plus b, plug everything in and be done, right? Y equal mx plus b, pick 4 and 6 because it has no negative numbers. You have 6 is equal to 14 times, who picked these numbers? Plus b, 14 times this, so that's a 56, that's what I said, and then it's negative 50, right? So y equals 14x minus 50, and you're done. So you have to be able to find the equation of the line given 2 points, because 2 points are all you need to define a line, right? So mathematically there has to be a way, and this is the way. Now, do we get to do this in 3D? Well, hell yes, right? The same problem in 3D is Teotel. Write the equation of the line given, and now I'm giving you 2 points in space, and those are 3D points, obviously. So 3, negative 1, 2, and 5, 6, and 7 for creativity, I guess. I don't know. Where do you begin? You begin by figuring out which one you want to be your point number 1 and point number 2. Is that important? Well, hell yes, it was important in your algebra class, because it was y2 minus y1, right, to get the slope. Now, why would it be important in Calc 3? Well, how do you get the slope for the Calc 3 line? What is it? What is the slope for Calc 3 line? Tell me from this picture. What is the slope for Calc 3 line? Which one? Yes, V. It's the V vector. And we know that when you are dealing with the V vector, you better know which one is your initial point and which was your terminal. Because to find the vector is terminal minus initial, right? You can't mix and match x's and y's in a slope equation in Algebra 1. You clearly need to know what's your y1 and what's your y2. Otherwise, you're doomed. You will be the same way doomed in Calc 3 if you do not clearly make to yourself which one is your point 1 and which one is your point 2. Because point 1 is like the source. Point 1 is like initial point, right? Everything starts there. So you pick what's your point 1, you pick what's point 2, so we can, do the job by, 1 and 2. As soon as you did that, V is 2 minus 1 to get the vector. So vector V immediately becomes 5 minus 3 is 2, 6 plus 1 is 7, and 7 minus 2 is 5. It's a terminal minus initial. And then you also, this is what I generally suggest to students, is to immediately copy the first point, right? Your initial, x0, y0, z0, because you need that one to plug in. You can't just pick any, right? So now you have your v, and you have your point, and from this point on, just x, y, z, and you have your equation. So 275 t plus 3 minus 1 plus 2, and you walk away.
Real quick, what did you do for vector v? 2 minus 1.
Yeah.
Where is that from?
0.2
0.2.
minus.
Oh, minus the 1.
Mm-hmm.
So you do 5 minus 2.
So we use the same point, right? I mean, once we do the terminal minus initial, we got the vector. And what do we
You need the initial for this. Remember, look at the picture. Look at the picture. Right? Which? Right? Good. So, guys, when you are learning Calc 3, don't start fresh. All right? These are not new concepts. These are the concepts redefined for 3D. We've seen earlier the distance formula adds a z term. When you compare the equation of the circle and equation of the sphere, you add the z term. The midpoint formula and the average for z, right? So we've seen that formulas just get expanded to accommodate for the new dimension. Now, equation for the straight line has to be equation for the straight line, and just, I don't care what amount of dimensions you have. But now that the vectors are driving everything, we have just a little bit different calculation, but it's still the same concept. You have 2 points, subtract the 2 points to get this 3D slope, and then use the initial point as your initial point over there, and put them all in the vector, and everyone is happy. Now, I mentioned earlier, and we are going to use this at some points in our class, the line segment is a part of the line. And you control that by cutting the t off, right? You cut the t, instead of going from negative infinity to positive infinity, you cut t to go from 1 to 5, or negative 1 to 6, whatever you need for your application, right? Most of the cases, it's like 0 to 1, but it could be anything else. And we are going to have all different types. So now, this equation of the line, this is your answer, assumes t that is in between negative infinity and positive infinity. And if you want to, be very precise about it, you would have to box both and say that's your answer, right? So this is your infinite line in 3D space. Now, we can make it into line segment by restricting t. So now, let's say t to be between 0 and 2. Let's say that's the, 0 to 2. And if that's the case, right, looking at the problem up there, right, you would have to rewrite it. 7t minus 1 and 5t plus 2. And you would have to include 0 less than t less than 2. Now, if this is the case, we have endpoints. So now we have endpoints. And you can calculate those endpoints easily by plugging in 0 and plugging it 2. So endpoints, I'll put the 2 dots. So t equals 0 is going to give us the initial point 3, negative 1, and 2. And then the endpoint on the other side is going to be when you plug in 2. So that's a 4, it's a 7, and it's a 14, it's a 13, and then it's a 10 and 12. Now you know how to graph these in space, and you just connect them with a straight line, making sure you have 2 points, right? 2 dots filled in on each of the ends, and then you have your line segment. Now that line segment obviously will lie on the infinite line, which goes from negative infinity to positive infinity. So as I said, we will be back using this thing. We don't need it now, but eventually it will kick in and we'll have to use it. Ready? Ready to discuss more stuff?
Yay.
That's the spirit. Just need to get my example. What's the equation of this? So, if this is stretched in space, I can go in my, use the grid that we established earlier, right? We know that the z-axis in this classroom is 10 feet high, and we have x and y axis on the floor. So I can measure this point here using the x, y, z in space. I can measure this point here. I give you 2 points, and we just did the equation of the line, right? And we can figure out what t will stretch between these 2 points, and I have the line segment, which is the length of this cable, right? Now what? Right? Now see, this is the power of Calc3. There is a way to figure out the equations for this as well. Now clearly it's going to be much more task, but the idea is that if you have the origin in the corner of the classroom, right there, there's going to be a vector r which stretches to each location in space. So there will be an x location, a y location, a z location, which is every point of this line. And that vector is going to point to each point one at a time until it traces the entire line. So now, as we are moving to talk about the curves in space, again, we are limiting ourselves to 3D because it's Calc 3. More of this linear algebra, you want infinite dimensions. So, curves in space. Space, there we go. Again, 3D. We are going to draw the 3D system. X, Y, Z. And we're going to draw some kind of a curve. And we are going to stretch the vector R, 0, and the vector R, which is going to follow along and hit every single point, not just the ones that I outlined. There are infinitely many points. You need to trace through all of them to draw this line. So what I'm going to do here is I'm going to again say vector valued function R, which is our vector, f of t, g of t, and h of t, also written as f of t I plus g of t j plus h of t k, if you want the ijk notation. And welcome to the curves in space. Now this is obviously a 3D case because we only have three functions, f, g, and h. Now if you take a look, what we did with a straight line has the same form, except all of these f, g, h functions are linear, and therefore the overall line is linear. What I'm going to do next is I'm going to start replacing f, g, and h with other functions, quadratic, square root, trigonometric, and so on, which is going to give rise to these curves in space. So we are going to have, again, the orientation of the curve because we have parametric equations. Now they are just arranged in a vector. So we are going to have orientation in direction of increasing t. And depending on what your functions are, clearly you're going to have different shapes. The first case of us working with this would be the helix. Helix is the simplest to understand because the first two coordinates, the first two entries in the vector, the first two functions will be the cosine and the sine, which give you the circle. And then the z is going to tell you in which way that circle evolves in time as it goes up. So what is the helix? Helix is a spring. You all seen spring in life. Otherwise, you shouldn't be really sitting in this class. So some of you took the cars apart and you know about shocks and things like that, right? Some of you took the pen apart, and some of you did much more electrical or mechanical engineering to find the spring somewhere, right? So we can describe the equation of the spring very easily by using this equation. So what do I have? I have a circle. So first I'm going to actually draw the isometric view over here. So x and the y. And I'm going to just draw this terrible helix going up. Actually, no, this is really good. It's just your eyes are terrible. That's why it's right. It's not the helix; it's your eyes. Now, if you look at the base of this helix, you are going to have a circle. So, top view is just going to be a circle on the xy plane. And again, you better understand this, because when you put the spring on the table and you look from the top, you just see a circle, right? So now, we know parametric equations for a circle, and that determines the yes, the x and the y coordinates of our parametric set for our vector valued function. So r is equal to, let's say it's 2 inches radius of the spring, so 2 cosine, so if this is at 2 and this is at 2, so 2 cosine t, 2 sine t, these are your x and the y, and now you can say t. Now if you say t, right, if you say t for your z component, you have a linear rise, which means you have a spring that you know. You can have a constant there. Are you going to have a helix if you have a constant?
No.
No. What are you going to have?
Circle with on a plane that's the constant height.
Very good. So I can describe this circle here, or pick any light that you can see above you. I can describe the circle, let's say this is, what is this, 2 inches, right? So this would be 2 cosine, 2 sine, t, and then just 10, comma 10, because it's 10 feet high, all right? So I just described a circle. There is no line going up, because everything is happening, it's completely contained. If I just want to show this line here, it's definitely, it's a 2-inch radius, 4-inch diameter. 2-inch radius is going to be 2 cosine t, 2 sine t, and then just comma 10. If I take it, put it on the floor, it's going to be comma 0, because we said floor is going to be 0 elevation, z equals 0, right? Now if you have t is the 45 degree, remember the y equal x, right? So t is the 45 degree incline. So the line for the helix is going to be climbing at the 45 degree going up. So you have x and y that are making circle, and then you have the z component to spiral it up forever and down. But we don't have to stop there. We can design whatever the hell spring we want. I can make the spring that it's going to start at maybe t squared. T squared is going to start wrapping like this, and it's going to actually rise much faster, right? So if you have a nice helix, which is your spring, right? But it's not all of the ends of the spring at all, right? You know how the ends of the springs are coiled next to each other, and then it goes into separation, and then they coil again. What do you think is that design? What is the formula for that? You're going to be mechanical engineers building those things and calculating stuff? Yeah, you see where that goes, right? So for that type of the, right, for the spring, you have the coil next to each other, and then it starts doing this, right?
Square root.
Square root of t. Right? So these are kind of things that you have to understand. You have to calculate the spring constant to have the thickness of the material to see which material is used. There is so much design in one spring that, right? Otherwise, we'll just have one type of spring, and then for the train, just use 10,000 of them, and for the pen, use one, right? Is that how it works? So, I know. So you have to compute these things, guys. And it needs to be machined. You have to have the drawing for it and the AutoCAD and everything. I mean, come on, you want to be engineers? You picked it, right? So now you go and learn. You can make this helix to be not circular. You can make it elliptical. How would you make an elliptical? Yes.
Would you change the coefficient in front of the cosine and the sine?
Yes. So they are not allowed to be what?
Zero.
Yeah, they can be 0, but they are not allowed to be what? So they are not circle. The same. So as long as you have these coefficients in front of sines and cosines, different numbers, it's going to be an ellipse and a base. Again, you better know that from PreCalc 2, you better know that from our review on the first day. So if the numbers are the same, it's a circular base. If the numbers are different, and it's not allowed to be 0. Good.
You can get like really cool stuff. Like you do like the 2 cosine of like 4t, and then do the little flowers, right? But like a I guess, and then with the t having an increase.
Yeah, but you only see the flower when you look from the top.
Well, you take what you can get.
That's true, because from the side it's just going to be the line going up.
Yeah.
But yeah. But yeah, you can, which is pretty good. And now, what else can I do? I'm going to ask you this now. What is R equals what is? Draw in your notes. Draw. R equals 3 cosine t, t, 3 sine t. You know you're allowed to talk to people that exist around you. And eventually I'll go around asking you to tell me their names. That includes people in front and behind.
Oh, yeah, yeah, you're right, yeah.
So it means, so should I draw y rises and you right? So we do it like this.
Yeah, you had it right. It just can't do it.
So it's gonna it rises. If this was like cosine t, it would be sine.
I was thinking about how weird it would be if you had 3 cosine t, 3 sine t, and 3 cosine t. You know, like thinking about that.
Like how the way
Everything's bounded. Would that just be a sphere? Right? It would be a sphere. That's what I was thinking about, because obviously it has to be bounded by. I think that's all this. But that makes sense because
no, this one comes all the way up.
mathematically the only one. I haven't actually looked on yeah. I haven't actually looked to see if it has anything.
So it's bigger. It's more
Yeah, so let's see what it looks like.
Yeah, that's the radius. As long as it's
Which way does it work? Which way?
yeah, it is.
I know, like, right? Yeah, it's what,
Pretty sure if it's negative t, then it was spiral
No, that's not what I meant. I meant which way did it spiral first? From, see how mine goes from right to left, I guess. And yours goes. So it's based off of which one. Well, let's see. It goes from t is 0, 0. So it has to start from the x side. Yeah, so it would go x to negative. Right?
So what's the verdict over here? What is this? It's a helix.
I just haven't switched.
My T is in the wrong spot, or it's not. What's going on?
It's rotated. It spirals around the y-axis.
Yes. So this is just a spring that is now
On the side.
Horizontally on the side, yes, on the desk. So it wraps around the y-axis because t is around the y-axis. So, to draw this, get our x, y, our z, and just spiral it around here. And that's all it is, right? Knowing that this height over here on z-axis is 3 and this number over here is 3 on the x as well, right? Bueno?
Oh, quick question.
Yes.
If all of them were trig functions in the front, would that make it a sphere? Like if it was 3 cosine t, 3 sine t, and then 3 cosine t, would that be a sphere? That is a sphere. Okay.
Without me drawing this, is this called a slinky?
I don't know why I find that funny.
Slinky. Say slinky. Slinky. Say it. There you go. Look at that. Slinky. Now, next time you see a child play with a thing, right?
Take it away.
Take it away.
They can explain what
You connect it, and if anyone starts screaming at you, you have equations to explain. And you say you can model it. You can, right? There are things. I know.
I would have just taken it away and said they could have it back once they can write me an equation for it.
I vote yes.
Poor 6-year-old child. At least he'll learn.
Exactly. And their entire life. Plus, they would probably make the movie about it later. You know, the journey of John. You know, going from the trauma when he was 6 years old to actually, you know, maturing and at a college learning the equations so he can finally get his slinky back.
That would be interesting.
And then probably can get the Dr. Phil to build up on it and give us the nonsense that no one cares about. Anyway, so we have that part. That's good. And
So I gotta go back.
guys, how about we do some calculus? We haven't done any.
Yeah.
Right?
Yeah.
Like past addition and multiplication and subtraction, I don't think we did anything else in this class yet.
Other than,
So,
you know, parametrics.
where's the calculus in there?
Well, I meant it's in calculus.
Yeah, so 3 concepts that create calculus, that build calculus are limits, derivatives, and integrals, right? So, limits of vector valued functions. Again, the honors section, honors students, you need to know the epsilon delta definition, right? The same for everyone. So we have the definition as per usual. So a vector valued function R approaches the limit L as t approaches A, written limit t goes to A of R of t equals L. Now, that's a vector. provided that the limit t goes to a is t minus L equals 0. So they're the same at that point. Now, before you all panic and run, if you know your Calc 1 limits, well, you're done, because this is just going to be 3 Calc 1 problems in right. So, say that your R of t as a vector valued function is given by t squared minus 2 sine pi t and e to the t minus 2, and you want to find the limit as time approaches 2 seconds of R of t. What do you do? What do you do? Yes?
Take the limit of each x, y, and z component.
Individually, separately. So you have 3 Calculus 1 problems to work on. It's individual, each dimension, each parametric equation is individual dimension, individual calculation. So you have 3 Calculus 1 limits to take. These all happen to be extremely easy, but, you know, we might find some spicier cases, but this is as simple as it gets. So what's the answer? What's the vector L? Well, plug in 2, because in all of these cases nothing weird happens. So 4 minus 2, first one is 2. Sine of 2 pi is 0, and e to the 0 is 1. So the limit is 2, 0, 1. Yeah, I'm sorry that you're disappointed.
Now, I don't have to write that out, like each one.
You can if you want to.
Only in Calc 1, you know.
Yeah, Calc 1, but now we would say that you know enough Calc 1 so you don't have to write it out, but if you have to, you have to. We can also claim continuity of the vector valued function if each individual function is continuous, and then you go again and refer back to Calc 1 rules, and you have 3 separate problems to work on. If one of the components is discontinued, the whole thing is discontinuous, right? So continuity vector valued function R of t is continuous at A if every function in right f of t, g of t, h of t is continuous at that point A. Again, each continuity is going to be taken care of by Calculus 1. So you have the 3 rules, right? The function has the value if the limit has the value and if the function is the same as the limit. So we recycle Calculus 1 100% in this case. And that's it. I hope you're not disappointed. Now you know that the lines in space and curves in space and limits and continuity all in one shot. Since we have time, which is we have 17 minutes, and we really can't push to the next lecture because we only have 17 minutes. Let's work out more examples, right? So something that you can do, and then I'll work it out and so on.
Oh, so what was that? The proof that the honors needed to know? Was it the
definition?
Okay.
Limits of V.
Yeah, I mean, yes, maybe it's continuity as well, probably.
Yep. So problem 18 is a beautiful problem. Solve Teotel. True. One, 3, negative 4. Parallel to the line r of t equals to 3 plus 4t, 5 minus t, and 7. What was the deal with parallel lines and slopes and things like that? Do you remember that stuff? Ah, same slope. Okay. So if it's the same slope in 2D case, what do we have to have the same in 3D?
Yeah.
We have to have the same, but what is the same in 3D case? Same direction vector V. Good. Go ahead. While we're still young. All right, that should be good enough for this one. What's vector v? Our direction vector, our slope vector, what is it? What is it?
Four 4t
negative 1,
and 0.
and 0. We see a 4t, right? So 4. We see negative 1 times t, so negative 1. And we see no t, so there had to be 0 times t to kill t, so 0. Are we all green on vector v? A, B, C, that it's always in front of t. It's AT, BT, CT. AT, BT, CT, right? So A is 4, B is negative 1, and C must be 0 because it killed t. Great. And then we have a point 1, 3, negative 4. So what's R? R is 4t plus 1, negative t plus 3, and negative 4.
In situations like, oh, never mind. I was going to say,
All right.
only because we have R used twice, but then we have R and then we have R. So, I don't know.
Problem 19. В Теотл. Through 0, 0, 0. Oh, this problem is so important. Perpendicular to both. Use orthogonal. Vector u 1, 0, 2 and v 0, 1, 1. Whew. What now?
Because both of them are taken in two different ways. The first one has a 0 for y, so it's a 1 and 2. The other one has a 0 for x, so it's 1 and 1. So that's how
What should I do to figure out the slope, the vector v? Cross product. Nice. The orthogonal vector to two vectors that are given produced by the cross product. So we have to cross u cross v. That's going to give us the vector, unfortunately again, v, right? And you have the point and you're done, right? So to find our vector v, you know what, I'm going to change this to w over here. It's going to be u cross w, which is, I know coughing, jk 1 0 2 0 1 1. So that's going to be negative, so it's going to be negative 2, and that's 1 negative 1, and then 1. Is this what we have for the cross product?
Yeah.
Good. And then you set up your line equation. So you have negative 2t plus 0, negative t, and t. They're all plus 0 because it goes to 0, 0, 0.
Good question.
Done. This is what it takes to do the problem in calculus.
Can you also put it in I, J, and K? It doesn't matter.
Yeah, negative 2i,
Yeah, it doesn't matter, right?
negative j, and plus k. But you need actually negative 2, negative 1, and 1 as numbers to plug it in for a, b, c for equation of the line.
Alright.
Why is it negative 1? Real quick. The center one, the second one.
It's negative j, right?
Oh, okay, never mind. That makes sense.
Was that a face palm that I missed? Or you snapped the fingers?
No, I snapped fingers.
Ah.
No, it doesn't
I
count.
don't know why I thought it was. I don't get it.
Yeah, it gives you the actual one.
And then I can do
This is useful.
Because I was thinking, I was eating like steak.
This might push us a little bit over time, but it's a very nice problem that you should consider. It has another problem just like it, and I like this problem a lot. Focused? Good. It says, determine the equation of the line that is perpendicular to two lines that are given and passes through their intersection.
Wow, okay.
So, we have the two lines given. So, Teotil, write the equation of the line. Perpendicular orthogonal, this is the perpendicular to r of t is given by negative 2 plus 3t, 2t, 3t, and another line, capital R of s, which is negative 6 plus s, negative 8 plus 2s, negative 12 plus 3s, so perpendicular to 2 of those and passes through the point of intersection. Three, yes. I'm not sure why I write 36, but at least one part is easy and one part is new, right? So what should we do to figure out the slope, the orientation? Very good. Of what? What am I supposed to cross to get the vector v for our line? Yes, as a notation, I need to cross VR with VR, right? So get there, it's 3, 2, 3. That needs to be crossed with 1, 2, 3. So these are the ABCs of both R, lowercase r, and capital R, right? So those vector valued functions, those are straight lines. They have their own vectors, right, of direction, which would be vectors v. So v lowercase r and v capital R, and those you extract those. So now we have that our v is given by ijk 3, 2, 3, 1, 2, 3. Right, these are all unit vectors, and we get this is 6 minus 6 is 0, and then we have 9 minus 3 is 6, so negative 6, and then we have 6 minus 2 is 4. Do we all have 0, negative 6, 4? Yes.
I'm confused about the part where you figured out what V is.
Which V? We have 3 V's. This V?
Yeah.
Because we said in the problem that the new line that you want to write needs to be orthogonal or perpendicular to the other 2 lines. Last class we said that if you have 2 vectors in space, the cross product of those 2 vectors is giving you the perpendicular one, which is the reason why we're taking the cross product of the directions of those 2 lines. Directions of the lines are encoded in their ABC slope, which are the numbers in front of t's. So the first vector is from the first line, 3, 2, 3. and the second vector 1, 2, 3 is from the second line.
So you just take the slopes then, and then just put that into the vector? Okay.
Guys, $1 million question now. How do we find the intersection of these two lines? Set to each other what? That's good.
Set them equal to each other?
Yes. How would you set them equal to each other?
Each x component, y component,
Yeah. So you set x to x component, and y to y, and z to z. Because in space, see, one line is governed by parameter s, the other one is governed by parameter t. What do they share in common? In order for them to intersect, they have to share common x-coordinate and common y-coordinate. So as I extract from r, which is given as negative 2 plus 3, negative 2 plus 3t, comma 2t, comma 3t. You see, what I extract from here is that x is equal negative 2 plus 3t, y is equal to t, z is equal to 3t. From the capital R, which is in terms of s parameter, I am extracting negative 6 plus s, negative 8 plus 2s, and negative 12 plus 3s, if I remember. So now those are vectors, and look, x is equal negative 6 plus s, y is equal negative 8 plus 2s, and z is equal to negative 12 plus 3s. So now, if I want to find the point of intersection, if the intersection is at 1, 2, 3, well, x-coordinate of both lowercase r and uppercase r better be 1, right? So I am setting negative 2 plus 3t to be the same as negative 6 plus s. Then I have 2t is equal to negative 8 plus 2s. This is the overdetermined system. So 3t is equal to negative 12 plus 3s. You don't have to use it. I mean, it has to match. If that doesn't fall, right? Because you have two variables and three equations. You don't need a third equation because your goal is to find s and t, right? Well, you can find any of them. So let's say you use the second two equations because is the second two equations cheap? No. It's first and third, right? First and third equations are cheap if you subtract them. So you do 3 minus 1. That's the fastest. So you have 2 equals, right? 3t minus 3t is 0. So 0 minus 2 is positive 2. 0 minus negative 2 is positive 2. And then you have 3s minus s is 2s. And negative 12 plus 6 is what? Negative 12 plus 6 is negative 6. So 2s is equal to 8, s equals to 4. So it seems that s is equal to 4. Now you should check it, but in interest of time, since we have s is equal to 4, you can plug s everywhere and get your point. So plug in.
Okay, you only have to find one.
Well, if they don't line up, if all others don't line up, then they don't intersect.
Oh, yeah.
Right? And that's a problem. I'm assuming that they're going to intersect because that's carefully crafted problem, but they don't have to. And then it's the issue. So now, when you plug that in, s being 4, you get point negative 2, 0, and 0. So now you can write your line as whatever, L of t, to be, or you can pick a different parameter, whatever, now t is equal to, what was our 0, negative 6, 4, so 0, negative 6, 4. There you go. So this problem had a lot of cool things going on. And you have another similar problem, and I hope something like this is included in your homework online. There's another problem like this, 49, with the answer in the back, if you can check when you do at home. This is a really good problem. You have intersection of lines in space. It's difficult to intersect lines in space, guys. There's only one way to mess it up in 2D. If they're parallel, right? Right? Imagine in how many ways you can mess up in 3D. Here's the first line, and here's the second line going this way, right? In 2D, they look like they intersect, but they don't. There's a gap in between, right? So it's called skewed lines. They pass through space. It's very difficult to get them to intersect, right?
Oh, yeah.
Where in 2D, you intersect them like this. There's only one case when they're not intersecting, and everywhere else they do. So there you have it. That's 11.5. Next class 11.6 and maybe 11.7. Definitely 11.7. We pushed through.
Are you done?